So the first law of thermodynamics states that the energy of the universe is constant. The second law of thermodynamics said that the entropy of the universe tends toward the maximum. In other words, the entropy of the universe is always increasing, or the change in entropy of the universe, delta S of the universe, is positive. The third law of thermodynamics says that the entropy of a pure crystal at 0 Kelvin is 0. Now that sounds like a really kind of a silly law, but what that does is it gives us a point to start all of our entropy measurements at. We're always comparing entropy measurements to the entropy of a pure crystal at 0 Kelvin, absolute zero. Now, the third law can get a little more tricky if you're dealing with things that have more than one crystal state. We have to deal with different things. Some things like glass can form more than one crystal structure, and so we'd have to look at, okay, which crystal structure is this because they have different values. We're not going to get into that in this class. That's much more advanced than what we're doing here. We'll just stick with saying that a pure crystal at 0 K is 0, which means that anything else has to have an entropy of greater than 0. And so what we use is a standard entropy. So the standard form at 298 K, that's room temperature, 25 degrees Celsius, and 1 bar instead of atmosphere. I know the notes say atmosphere. The definition has recently changed to 1 bar instead of 1 atmosphere. It's very little difference. So what we do is we take the entropy of the products minus the entropy of the reactants to find the change in entropy at standard state, delta S 0, which means this is a state function. We don't care about how it got from products or from reactants to products. All we care about is where it started and where it ended. Now, of course, the more complex the molecule you have, the higher the standard entropy, because they can twist and turn and form more complex shapes. Not that the shapes themselves are more complex, they can form more shapes that are also complex. So the more bonds you have inside something, the higher the delta S. We can also define a standard free energy change, Gibbs free energy change, delta G, 0. The 0 always means in their standard states at room temperature. So if we have standard state reaction happening, for example, if we're reacting hydrogen plus oxygen to make water, we look at those changes in terms of their standard states. If you burn hydrogen oxygen in air, you're going to end up with water vapor. And that's not water standard state. Water standard state is liquid. So what we have to imagine then is we burn hydrogen oxygen, and then we collect all that water vapor and cool it down to liquid water. And then we measure it. Okay? And we're not going to measure, we can't measure Gibbs free energy directly. We have to calculate from the delta H 0 and the delta S 0. So how do we calculate those things? We use Hess's law. All right, where there's tables in the back of your book, the big, huge, thick CRC book that I have, all these have these values. We can look them up and determine the delta G0 and find out if the reaction will be spontaneous or not. Again, look up those tables, delta G of formation, and we're going to use Hess's law with delta G just like we did with delta H. So any element in its standard state is going to have a standard free energy of formation of 0 because it took no work to form an element because the element is the most basic form. And we can do all of our calculations following Hess's law. Hess's law works for all state functions, not just enthalpy. Now remember, just because something's spontaneous doesn't tell us how fast it's going to be. And we like to think of something spontaneous as being quick or easy. If you put an ice cube out to melt at plus 0.01 degrees Celsius, it will melt spontaneously, but it will melt very, very slowly. Okay? Spontaneity has no relationship to rate of change.